Now we will start sound waves. So what are sound waves? How is sound produced? So sound waves are produced by the vibrations of the particles of any medium. So what are sound waves and how are they produced? So sound waves are the vibrations of the particles of any medium. So if you have any medium, for example air, water, anything, so when the particles of those mediums vibrate, then sound is produced. The sound waves usually are longitudinal in nature. Transverse waves look like this and longitudinal waves look like this. So sound waves are usually longitudinal in nature. There are compressions and rarefactions. The compressions travel in a medium at a speed which depends on the elasticity and the inertial properties of the medium. So the compression or rarefaction that travels in the medium depend on inertial and elastic properties of the medium. So as discussed previously as well, the wave is produced because of either inertia or because of the elasticity. So this inertial or elastic properties helps the compression or rarefactions to travel through the medium, and as the source moves back, it drags the medium and produces a refraction in the layer, rarefaction in the layer. So compression travels, then the source moves back, then a rarefaction is produced. So compression and rarefactions are produced because of the inertial and elastic properties. So for example, let's suppose we have a container or a room. Let's say this is a room and we have a lot of air particles in this room. A lot of air particles in this room are there. Now what happens is that let's say because of anything, let's say we call it a source. So because of any source there is some vibration. So there is some vibration that is produced by, let's say there is a source, and that vibration tries to vibrate the particles of the medium. So let's say the particles of the air starts to vibrate, so they will start to vibrate. Now when they vibrate, they will try to vibrate the nearby particles. The vibration will travel, and when the source moves back just a little bit, so then the rarefaction will be produced. So the waves will be like this. So at some places waves will be close, vibrations will be close, and at some places vibrations will be far off. So it looks like this approximately. It looks something like this. So these are called compressions, these are rarefactions, then compressions. So the compressions and rarefactions are alternative. Okay, so when the source vibrate, rarefactions are produced. Then when the source moves back, so then the rarefaction is produced, compression is produced. So compression, then rarefaction, compression, then rarefaction. So this is how the sound is traveling in a medium. Sound is the vibration of the particles of the medium. Now what is the formula for the displacement of the sound wave? So the sound is moving forward. Okay, the vibration is moving forward. The particles remain at, usually the particles remain at their location, but the vibration is traveling. So the displacement of those particles can be given by this equation. So this is a usual wave equation where S naught is the maximum value of the displacement, maximum displacement, or it can be also said it is the amplitude. S is the displacement at any time period t and at any location x, and sine is the variation with time t. It tells us about the variation of the wave with time t and with displacement x. So this is the equation for displacement. So now let's suppose we have this element we are considering a region in which the sound wave is traveling. So let's say initially the vibration was here in this region, and it then traveled from this region to this region and it expanded. So let's say the displacement was s here and the displacement is s plus del s here, and this is x and this is x plus del x. So let's say the vibrations are traveling in the medium, and let's say the area of this region is A. So what will be the increase in the volume of this element when the vibrations travel? So the increase in the volume will be area into the increase in the displacement, okay, or increase in the position, change in the position. So this will be area into length, okay. So now we know that change in the position with respect to time, okay, it can be obtained by differentiating. So del s can be obtained by differentiating this. So the differentiation of sine will be cos, okay. So the differentiation of sine will be cos, then same omega t minus x by v. Now when we differentiate, so there will be this term also s naught, which is the amplitude, and this we are differentiating with respect to t, so there will be this omega and v also, which will remain. So minus omega upon v will remain, and here del x will be there. So this will be the change in the volume, increase in the volume. Now let's try to find the ratio. So the change in volume with respect to original volume, so it will tell us about the amount of change in the volume. So now let's say, so if the volume is increased, so there will be some strain. When something increase, then let's say you increase the spring size of this spring, so this spring will now be in a strain, okay, the string will try to compress. So similarly, if the volume is increasing, then there will be some strain. So the strain is change in the volume upon original volume, so that will be minus. Why minus? Because it will try to reduce the volume. So s naught omega and cos omega t minus x by v del x. So just the value here. So again reminding you, here del s, so how did we find del s? It is the change in s with respect to x, it is a change in s with respect to x. Now dividing it by v, so now we know that volume can be written like, here we need to also have the x component as well. So here x component will also be there. So because of that x component, we will have v into a del x, where v is the velocity. Now after this a bit of simplification and we will get this thing. So now this is the strain. So what will be the stress? So this is the strain. What will be the stress? So the corresponding stress can be obtained by excess pressure. So the excess pressure is beta minus del v by v, and here again we know what is minus del v by v. It will be s naught omega by v cos omega t minus x by v. And here we can consider that this thing b omega by v into s naught, this thing is p naught. This is the pressure amplitude. We can consider it to be pressure amplitude, or we can write it b k s naught. So this is the pressure amplitude maximum value of the pressure. This is the propagation constant, where its value is omega upon v, and it is sometimes also called the wave number. K is also called the wave number. So let's just, for now, let's only write it as the wave number. So this is the formula for the stress or strain or the displacement when the particle is traveling in the medium. So sound is produced by the change in the pressure, it is produced by the vibration of the particles of any medium. So now we can also find the speed of sound as well, speed of sound. So we will try to write speed of sound in different materials. So the general formula for the speed of sound is V equal to root B by rho. Here B is the bulk modulus. We discussed the bulk modulus in the chapter where we discuss about mechanics of solid, and rho is the density of the medium. This is a general basic formula. So now, but let's try to write the speed in various mediums, speed of sound in various mediums. So first in solids and then in gases. So in solids, the speed of sound can be usually found out using the following formula: V equal to root Y by rho, where again Y is the Young's modulus and rho is the density of solid. So instead of bulk modulus, we will have Young's modulus in the case of solids. Now the speed of sound in various medium is given, like for example, speed of sound in air is approximately 332 meter per second at 0 degree Celsius. Speed of sound in hydrogen is 13330 meter per second, because hydrogen is less dense, so the particles move a bit quickly. Then speed of sound in water is 1486 meter per second. Then the speed of sound in copper is 3810 meter per second. Speed of sound in aluminum is 5000 meter per second, and speed of sound in steel is approximately 5200 meter per second. These are all approximate values, but one thing you can observe is that the speed of sound is more in the denser medium as opposed to the rarer medium. So as the density increase, the speed of sound waves increase. So more the density, more will be the speed. So density and speed of sound are related. Now similarly, the velocity of sound in gases was first given by Newton. Newton proposed that the velocity must be equal to P by rho, where P is the pressure of the gas and rho is the density. But it was found out that this formula does not give the exact value. So then there was a mathematician called Laplace. So Laplace corrected this formula and he introduced another term called gamma. This gamma is the term which will be introduced in thermodynamics. Gamma is the ratio of Cp upon Cv, specific heat at constant pressure upon specific heat at constant volume. So this will be introduced in thermodynamics. So Laplace corrected this formula and he used this formula to correctly predict the speed of sound in the gases. Now let's discuss another formula, and that is of the intensity of sound. Intensity of sound. So before we jump to the formula, what is the meaning of intensity? So intensity tells us about the an average energy crossing a unit cross sectional area perpendicular to the direction of propagation of wave in unit time. Or in simple terms, let's say we have this region, let's say we have this region, let's say its area is 1 meter square. So what is intensity? Intensity is the amount of energy which is incident on a unit area in, let's say, per second, in 1 second. Then that term, that in energy, is called intensity. So energy per unit area per unit time is called the intensity. So if more energy is coming on a particular region, then intensity will be more, and if less energy is coming on a particular area, then the intensity will be less. So the formula for intensity of sound is V upon 2 rho V square P naught square, or you can simplify this to be P naught square upon 2 rho V, where P naught is the pressure amplitude, the maximum value of the pressure amplitude. So this is the maximum value of the pressure in the medium. Rho is the density of the medium, and V is the velocity of sound in the medium. So the intensity of sound can be obtained using this formula as well. So intensity tells us about the energy which is incident on a unit area in a unit time interval. So more the energy, more will be the intensity. Now let's try to discuss how the human ear perceives sound. Human ear and sound. So there are a few properties which our human ear can perceive. Okay, so what are those properties? So those properties are: first, pitch and frequency; second, loudness and intensity; and third is the quality and waveform. So these are the things that our human ear can interpret, and using these three major properties, we differentiate various sounds. We differentiate the sound of piano from the sound of guitar. We differentiate the sound of a human from the sound of dog. So because of these three properties, we can differentiate various different sounds. So what is the pitch, and what is loudness, what is quality? So first of all, pitch of a sound is a sensation by which we differentiate a buffalo voice with a male voice with a female voice. So the pitch of every body is different. In general, pitch tells us about the frequency, or you can say frequency tells us about the pitch. So if somebody has high pitch, for example, in a male voice, okay, and if somebody has a even higher pitch, or we can say that let's try to only discuss about humans. So in humans, the females have high pitch voice, and males have comparatively low pitch voice. So high pitch means the frequency is high. High pitch means the frequency is high, and low pitch means the frequency is low. So the frequency change can help us in finding whether it is a female voice or a male voice. So frequency is the basic property which is helping us in differentiating, but we have given it a name called pitch. you can say that frequency is the scientific name and pitch is the general name. So frequency and pitch are same thing. So frequency tells us about whether the sound is of a female or a male. So frequency helps us in differentiating the sounds. High frequency means high pitch, low frequency means low pitch. Now similarly we have this concept of loudness. So what is loudness? So loudness is related to the intensity. So let's say we have again let me first write loudness is related with intensity. So again you can say intensity is the scientific name kind of thing, and loudness is the general term that we use in day to day life. So if usually if the intensity is more, it means that the loudness of the sound will be more, sound will be louder. And if the intensity is less, then it means the loudness of the sound will be less. So we are not discussing about the frequency here, remember, okay, we are discussing about the energy per unit area per unit time that is coming. So more the energy coming, more will be the loudness, less energy that is coming, less will be the loudness. So loudness can help us in differentiating different sounds. For example, the sound of the plane is very loud, whereas the sound of a pin dropping on a surface is very less. So the loudness tells us about the intensity, or you can say intensity tells us about the loudness. Now similarly we have this concept of quality or timbre. So this quality depends on the waveform, shape of the waveform. So there can be same pitch, there can be same frequency, there can be same loudness, but still you can differentiate the sound between guitar and a piano. So let's say we are playing C chord on guitar and C chord on piano. So still the frequency and everything is same, but what is different, the waveform, shape of the waveform is different. So let's say the waveform in one case is something like this, and the waveform in second case is, let's say, something like this. So the difference in the waveform can also help us in differentiating the sound of various objects. So this is called the quality or the timbre of the sound. Usually if there is soft turns like this, then the sound is a bit soothing to hear, and so when there is some sudden transitions like this, then the sound is a bit harsh. Usually rock band sound is like this, and acoustic guitar sound is like this. So these are the properties which help us in differentiating different types of sounds. So human ear can differentiate sound because of pitch, loudness and the quality. Now the sound waves are reflected, they can reflect. So the reflection of sound waves can generate a different type of phenomena. So first let's try to discuss about the reflection of sound waves, and then we will move on to the phenomena that the reflection cause. So the sound waves when traveling through a medium, they can reflect back from a surface, and when the sound waves reflect back from a surface in the same medium, then we say that it is reflection of sound. When sound waves bounce back in the same medium, then we say that it is the reflection of sound. So reflection of sound is the bouncing back of vibrations or sound waves in the same medium. So let's say we have standing waves. So in standing waves, the concept of reflection is very important. So as discussed previously, what are standing waves? So let's say we have a wave which is traveling in this direction, and then let's say there is a surface here, so the wave may get reflected from here. So there can be a reflected wave also. So what will happen, we can have a situation in which we have such a wave which looks like this, which looks something like this, in which few points become nodes permanently, that is their amplitude do not change, and few points remain in the antinode location where the amplitude varies a lot, the value of displacement is a lot. So the standing waves can be produced because of the reflection of light. So when reflection of sound, so when the sound is moving like this and the reflected sound is there, so if the conditions are good, conditions are proper, then we can observe standing waves. So those standing waves can be produced, can be obtained in two types of devices. They are called the organ pipes. The standing waves can be observed in the organ pipes. There is two types of organ pipes: open organ pipe and a closed organ pipe. So the open organ pipe is a organ pipe which is like an open tube, okay, open tube. And a closed organ pipe is a device in which one of the uh, region is closed and the sound can go from one of the sides. So in open both the ends are open, in closed one end is open, one end is closed. So this organ pipes produce a different types of waves. So let's discuss about that. So in the open organ pipe, both the ends will be open, in closed one end will be closed and one will be open. So what you need to remember is that when, let's say, first we will consider open organ pipe. So when there is open end, remember this, when there is open end there will be antinode, and when there is closed end there will be node. So let's say uh, here antinode will be there and node will be here on the closed end. So on the closed end node must be there, and on the open end there must be antinode. So antinode and node, maximum amplitude is antinode and minimum amplitude is node. Let me write it here. Node is minimum amplitude and antinode is maximum amplitude. Now let's first discuss about the open organ pipe. So in open organ pipe both the ends are open, so both the ends will have antinodes. So let's discuss the first one. So first situation is like this, the first thing can be like this. So here let's say the length of the tube organ pipe is L. So here L is equal to lambda by 2. How? Because this is lambda by 4 and this is lambda by 4. So this complete wave is lambda by 2. So this means lambda is equal to 2L. Okay, one complete wavelength is equal to twice the length of the organ pipe. So the frequency is velocity upon wavelength. So this will mean V upon 2L. So the frequency in the first situation is V by 2L. Now what if we have the second situation in which we have this kind of a structure, this kind of standing wave? So here length is equal to lambda. How? Because this is lambda by 4, this is lambda by 4 and this is lambda by 2. So it will give us lambda. So in this situation L is equal to lambda. So Ft will be V by lambda, that is V by L, or you can also write it 2 multiply and divide. So V by 2L is F1, so you can also write it 2F1, twice of F1. Now next, let's say the wave looks like, standing wave looks like this. So in this case, if you again further see, F will be 3F, F3 will be 3F1. So what we are obtaining is that F2 is 2F1, F3 is 3F1. So this is telling us that there is some proper relation between different frequencies with the fundamental of first frequency. F1 is the fundamental frequency. So because of that we write it like this: F1 is V by 2L, F2 is 2F1, F3 is 3F1, F4 is 4F1. So this is called the overtone. So first overtone, second overtone, third overtone and fourth overtone. So overtone is the sequence in which the frequency is there. Okay, if the overtone is 1, there is only one node. If overtone is 2, there are 2 nodes. If overtone is 3, there are 3 nodes. So this is first, second, third overtone. And what are harmonics? So this is the fundamental first harmonic. So this is twice of fundamental, so this is second harmonic. This is thrice of fundamental, so this is third harmonic. This is 4 times of fundamental, so this is the fourth harmonic. Now let's discuss about the closed organ pipe. This was the open organ pipe. Now let's discuss about the closed organ pipe. So in closed organ pipe, one end will be antinode, node, and one end will be antinode. So here let's say the first situation is like this, where L is equal to lambda by 4. This is lambda by 4. So lambda is 4L. So again V upon lambda, that is V upon 4L. So F1 is V upon 4L. Now second situation will be like this. So here L is equal to 3 lambda by 4. So lambda is 4L by 3. F3 will be 3V by 4L, and you can see F3 will be 3F1. Now why F3, why not F2, I will tell you. Let's write it only F. Let me tell you F3 because this is thrice of F1. Then similarly F5 will be 5 times F1. So what is happening here, in this case we do not have, so in this case F2 is not there, that is there is no such thing as twice of F1. Okay, so F3 is there, there is no F4, directly F5 is there because of this structure. Okay, because of this structure. So ultimately in closed organ pipe we have first overtone, second overtone, third overtone. This is quite simple, same thing. Okay, overtone. So here what is happening is 1 loop, 2 loop, 3 loop. Okay, so first, second, third overtone. But harmonics, so this is the fundamental basic harmonic. Now this is 3 times of fundamental, therefore this is third harmonic. This is 5 times the fundamental, therefore it is fifth harmonic. So in closed organ pipe there will be first, third and fifth harmonic. There will be no even harmonic. Okay, so this is closed and open organ pipe. So whenever these standing waves are produced because of the reflection of sound, so in organ pipes these weird things are observed, and these are very important in music theory.